Capacitance is a property of the configuration of two isolated electrodes. Capacitors maintain charge separation, create electric fields, and store electric potential energy. They're a common component in modern technology, from electric circuits to motors. So how do we describe the physics of capacitors? That's the topic of this video. To start, what is capacitance? To answer that question, let's consider the components necessary to build a capacitor. A capacitor consists of two isolated charge electrodes, one with plus Q of charge and the other with minus Q of charge. As we know, in a region surrounding a charged object, there is an electric field. The electric field points from the positive electrode to the negative electrode. Likewise, due to the electric field, there is a potential difference between the two electrodes. The capacitance is defined as the ratio of this potential difference to the charge on the positive plate. So what are the units of capacitance? According to the defining equation, it is a coulomb per volt. In honor of Michael Faraday, we call this combination a farad. 1 farad of capacitance is an enormous quantity. It used to take an entire room to hold a 1 farad capacitor. Typical capacitors you will find in the wild are measured in microfarads or picofarads. In spite of the defining equation, the capacitance is a purely geometric quantity. It depends just on the shape and orientation of the electrodes, and not on their charge. Let's look at a specific example. So here we have a parallel plate capacitor. Recall that the electric field between two infinite sheets of charge plus and minus sigma is a constant E equals sigma over epsilon naught, pointed from the positive plate to the negative plate. For our parallel plate capacitor, we will choose a plate area A and a plate separation D. The first step to determine the capacitance is to determine the electric field. We've already completed that step, since we need to find the potential difference between the two plates. Since the electric field is a constant, we can easily find the potential difference by multiplying the electric field by the distance between the plates. Delta V equals sigma D over epsilon naught. Next, we need to find the total charge on the positive plate. Since we're given the surface charge density sigma, we will multiply this density by the surface area of one plate to get the total charge, Q equals sigma times A. Finally, we take the ratio to get the capacitance. Notice how the capacitance only depends on the separation distance D in the area of the plates A. Also notice the role played by epsilon naught. According to dimensional analysis of this equation, the units of epsilon naught can also be written as a farad per meter. The permittivity of free space gives a sense of how well the medium can support electric field lines. We'll come back to this point when we discuss dielectrics. Not only do capacitors maintain a charge separation between the two electrodes, they can also store electric potential energy. That energy is stored directly in the field. We can associate it with the work done by an external force to produce the charge separation by moving electrons from one plate to the other. One way to calculate this work is by considering the average force necessary to move the charge. At the end of the day, we arrive at a formula for the stored electric potential energy in the capacitor field. Notice we can use the capacitor equation to show these two equations are equal to each other. Thus far, the insulating material between the electrodes of the capacitor has been air. But what if we insert a different material? We'll explore what happens when a conductor is inserted between the plates, but first we'll look at the behavior of an insulator. In an unpolarized insulator, the dipoles are randomly oriented and thus do not produce a net electric field. Now that they are aligned, however, they produce a dipole field that is directly opposite to the applied external field. Thus, by superposition, the net electric field will be diminished by the dipole field in the insulator because they are in an opposite direction. So again, here we have our capacitor, the electric field pointed downwards with some strength. When I insert my dielectric, I'll align the dipoles, and I'll produce a dipole field in the opposite direction. And when I add these together, I get a diminished electric field. One way to describe how the insulator is modifying the electric field is by changing the permittivity of free space to the permittivity of the medium. The dielectric constant K increases the permittivity of free space to the permittivity of the medium. By making this substitution in the capacitance equation, we can see that the capacitance will increase by inserting a dielectric material. But doesn't this seem counterintuitive? The dielectric is reducing the net electric field inside. How is it increasing the capacitance? Two things. First, Capacitance is purely a geometric property independent of the electric field or charges on the capacitor. Second, by reducing the electric field, the capacitor would need to compensate with a larger charge separation to get the same field and thus the same potential difference. So if you inserted a dielectric into a capacitor hooked up to an external power supply, more charge will move from one plate through the potential supply to the other to maintain the same potential difference across the capacitor. Another important material property of a dielectric is called the dielectric strength. It indicates the maximum electric field before the insulator turns into a conductor. In other words, charge will flow across the material. You're familiar with this breakdown voltage when you see a spark of electricity when you grab a doorknob after rubbing your feet along the carpet. Now, for the next set of questions, take the time to actively participate. After I read through the question, pause the video to record your answer. I'll then play 3 explanations justifying each of the answers. Pause the video again and see which one you agree with, and make a note if you changed your mind. Finally, I'll go through and explain the final answer fully. So for our first question, consider 2 capacitors, each having plate separation D. In each case, a slab of metal of thickness d/3 is inserted between the plates. In case A, the one currently shown, the slab is not connected to either plate. In case B, it is connected to the upper plate with a conducting wire. The capacitance is higher for case A, case B, or the 2 capacitances are equal. Here's what student 1 had to say about this question. I think case A is the higher capacitance. It's higher because we've inserted material into the electric field, which changes the permittivity of free space. Student 2 says, I think case B is the higher capacitance. It's higher because now there is 2 capacitors. And student 3 says, I think they're the same. Even though the charge moves from the top plate to the metal slab, everything will balance out. Which of these students do you think is right? First, we want to consider the effect of inserting a metal slab into the space between the capacitor where there is an electric field. Because metal is a conductor, the electric field in the meat of the slab will be 0. There will be an induced charge separation, but it will perfectly cancel out the field inside the metal. Thus, we can't think of this situation as being a dielectric insulator inserted into the medium. In case A, the charge separation creates 2 capacitors that are connected in series. Each capacitor has an area A and a separation distance d/3. In case B, connecting the slab to the top plate would cause all the charge to move from the top plate into the bottom surface of the slab. Thus, there is just 1 capacitor with area A and a separation distance d/3. Since the potential difference across both setups is the same, the capacitance of B is greater than the capacitance of A. Our next question. Consider a capacitor made of 2 parallel plates separated by distance d. The top plate has a surface charge density sigma, and the bottom plate minus sigma. A slab of metal of thickness L less than d is inserted between the plates, not connected to either one. Upon insertion of the metal slab, the potential difference between the plates increases, decreases, or remains the same. Here's what student 1 had to say. I think the potential difference increases because by inserting the metal slab, we increase the capacitance like in the previous question. Student 2 adds, I think the potential difference decreases because by inserting the metal slab, we change the electric field inside the region of the metal to 0. And student 3 comments, I think the potential difference doesn't change because the charge on each plate doesn't change by bringing in a metal slab without making contact. So what do you think? One way to think of this question is to consider what happens when we insert the metal slab. As the metal slab starts to enter the region where the electric field is non-zero, it will become polarized. As we know, polarization forces are attractive, and the metal slab will have a net force towards the middle of the capacitor region. Thus, the electric field of the capacitor will do positive work as the metal slab moves from outside the capacitor to inside. In order for the capacitor to do positive work, the potential energy of the capacitor must decrease. If the potential energy decreases, then the potential difference decreases as well. Another way to determine the potential difference with the metal slab inserted is by direct calculation. The electric field in the region of space outside the metal slab is still uniform and depends on the charge on the electrodes. The electric field inside the region of space where the metal slab is will be zero because the metal is a conductor. Since the potential difference across a uniform field is the electric field times the distance, if we go from a potential difference of ED to E times D minus L, since there is no contribution from the path length inside the conductor, and thus the potential difference will decrease. For our next question, you charge a parallel plate capacitor by connecting it to a battery of potential difference delta V naught. You then disconnect the battery. If the separation distance D between the plates increases, do the following quantities increase, decrease, or remain the same? The charge Q on each plate, the capacitance of the parallel plate capacitor, the potential difference across the plates, and the stored electrostatic energy. So take a second to jot down what your answers are. The key to solving a question like this is to identify which quantities in the capacitor equation is the constant. The rest of the quantities will follow. In this case, since we disconnect the constant potential source, it is the charge in each plate that will remain the same. Next, we can determine the behavior of the capacitance. Since the separation distance D is increased, the capacitance is decreased. Now, to tackle the potential difference across the plates. According to the capacitor equation, if the charge is a constant and the capacitance decreases, the potential difference will increase. Again, we can think of this according to the electric field remaining a constant, but the distance increasing. The last quantity to tackle is the stored electrostatic energy. We'll use the version of the equation with charge and capacitance in it. We see that if the charge is a constant and the capacitance is increasing, then the potential energy will increase. One way to think of this is the work done by the electric force on each plate as the separation distance increases. Since the force is attractive and the displacement is in the opposite direction, this work is negative. Since potential energy is negative the work, then the potential energy is increasing. Next, let's look at a similar situation. You charge a parallel plate capacitor by connecting it to a battery of potential difference delta V naught. Without disconnecting the battery, the separation distance D between the plates is increased. Do the following quantities increase, decrease, or remain the same? The charge Q on each plate, the capacitance of the parallel plate capacitor, the potential difference across the plates, or the stored electrostatic energy. Again, take a second to jot down what your answers are. Again, the key to solving a question like this is to identify which quantity in the capacitor equation is the constant. The rest of the quantities will follow. In this case, since we keep the constant potential difference source connected, it is the potential difference across the plate that will remain the same. Next, we can determine the behavior of the capacitance. Since the separation distance D is increased, the capacitance is decreased. Now to tackle the charge of the plates. According to the capacitor equation, if the potential difference is a constant and the capacitance decreases, the charge will decrease. The excess electrons will move through the potential source to the positive plate and diminish the charge. The last quantity we want to tackle is the stored electrostatic energy. We'll use the version of the equation with potential difference and capacitance in it. We see that if the potential difference is a constant and the capacitance is decreasing, then the potential difference will decrease. Why is that? One way to think of this is as the plates are separated and the charge decreases, the electric field decreases in strength. Since the potential energy is stored in the electric field, as the electric field approaches zero, the stored energy will too. Capacitors play an integral role in modern life by providing sources of constant electric fields and stored electric energy. Thanks for watching, and see you next time.